Alright, in this video I'm going to go over some technical improvements that are coming down the pipe for D3. Undercuts has really been the strong suit of this software in that the fits have been exceptional for quite some time, but the downside is that the refractory model process has been slow. For a fast, simple model like this one that's well horseshoed, where the blockout doesn't have a lot to do, it'd be maybe 35-40 seconds. In tough cases where if your insertion axis was pretty far off the height of the model, it was having to block out long areas, it could take over 2 minutes. So this is the new algorithm that I might be rolling out. I'm hesitant to roll out a new algorithm because I worry that the calibration of the fits, people's values are going to change, but once they change, they'll stay consistent after that. But enough about that. Let's just show it in action. All right. So first, we'll just do a straight blockout with no offsetting. So this will just remove everything underneath the height of contour. And we've got some printouts here that talk about what it's doing. So it takes about a little under 7 seconds to calculate all the undercuts and do the work. And then I do an optimization pass on the mesh after that, a little under 4. So we're at 10.5, or let's call it 11 seconds to block out the model. You see if we select this, you can see how closely the model is overlaying the original, but with undercuts removed. All right, I'm going to hide that one. And first, let's make sure we're at the same insertion axis. And now we will block it out again, but we will allow undercuts, and we'll allow up to 100 microns of undercut. And this should take about the same amount of time, maybe an extra second or two once we start putting in offsets and undercuts. So yeah, there it took 9 seconds to do the work and 7 seconds to optimize. So 16, so we'll call that 7, so 17.5 seconds to do something a little more complicated, and that's to selectively remove undercuts. Okay, because it's not just, you don't just have to find the undercut, so detecting undercut or not is pretty easy, but in this situation we actually have to evaluate how far undercut the portion of the model is. So now if I unhide the original one, you can see where the blockout changes in the height of contour. And if we run the ruler and protractor here and set it on thickness, we should get 0.1 everywhere we go here. So that's 0.099, it's 0.099, 0.097, 0.099, 0.099, 0.0997. So we everywhere, and sorry, what we're measuring, in case it's not clear with that terribly tiny text there, what we're measuring is the step from the height of contour in the full blockout model to the allowable undercut. So this is, a lot of softwares will block out undercuts based on the angle of the face. That's fine, but I find that the way we were trained is using the little surveyor arm, where you drop that height of contour down to a specified depth. And that's what I like about my algorithm, is that it follows that same principle. So and other softwares I'm sure work the same way, but I do know that some only block out based on the severity of the angle. Okay, so we showed pure undercut and then just block out with some undercut. So let's hide that one and hide that one. Let's put our view back to the same axis. Select the model, and finally let's give ourselves 200 microns of passive spacer and 100 microns of allowable undercut, and make sure we select to use both. And again, all these settings, these settings will be more or less hidden from the user because we'll be doing a particular task for a splint. Now when it comes time to do custom trays and other things like that, different parts of this algorithm will be exposed. But what's good about this is they've made it very robust in terms of the parameters that it accepts, and it behaves more or less the same way. So here we are, 10 seconds to do the math and 7 seconds to optimize the mesh, and that's pretty consistent depending on if we're offsetting, allowing undercut. The fastest one is just pure blockout. So here we have an even offset spacer, and then still undercuts above a certain amount blocked out. So another cool thing is, as I was just talking about, and this scene's probably getting pretty heavy. Just a couple million tries. Another thing that I was mentioning is that this algorithm is a little more robust. My previous one was highly optimized for offsets between 0.05 and 0.2, and it really failed beyond those. And so like if you wanted to make a custom tray or add more spacer to make a dual layer splint, it really wouldn't let you do that because the way the algorithm was constructed, it just wasn't set up for it. So this one's a little bit, not a little bit, a lot of it more robust. So let's give ourselves a 1 millimeter offset as if we were going to make a shell that needed to be relined. And then we don't even need to bother with the undercuts at that point because, well, sure, let's block out the undercuts, but we really don't need to bother with that because it's all going to get absorbed in the offset surface. Great, so again, we're right here at 17 seconds, so 16.6, and there you have it. It creates a watertight mesh. The surface looks great. The undercuts are extremely precise, and I only have to do a little bit of optimization passes at the end, whereas the other one I was having to comb the whole surface again and measure the offset to make sure that it was uniform and do some little corrections and spacing. In this case, I don't. Here we've got a near perfect 1 millimeter spacing, and so I'm very proud of this. This is a 4 or 5 years of experience and experimentation and coming to fruition, and I look forward to getting this into the final version of D3SPlint, which will be coming out in a month or two.